Hey guys, it's Sakanya. In today's video, we're going to be taking a look at this very tricky integral problem, and that is integration 0 to 1 of x times tan inverse of x squared dx. And I will say it is very tricky. It took me a while to figure out the correct answer, but if you feel confident that you could solve it, then pause this video, give this problem a go. And if you get stuck or you want to know how to solve it, then I will go over the solution right now. So I will give you a hint. We are going to be using integration by parts. And for those of you who don't know integration by parts, no worries. I'll do a quick little crash course so we're both on the same page. Integration by parts basically says that you need to identify two functions, and then using those two functions, you can break this integral into more manageable sizes or something that's easier to solve. So first is to identify what our two functions are going to be. You can only have two functions. So I'm thinking that the only two functions we see here are x and tan inverse x squared. So basically this function and this whole function right over here. Those are going to be our two functions. But that's not it. We also need to identify which is going to be our first function and which is going to be our second function. So what I mean by that is that our first function can either be x, and then our second function will have to be tan inverse x squared. Or we could do it the other way. Our first function can be tan inverse x squared, and our second function, of course, will have to be x. So why does it matter what our first function is and what our second function is if in both cases we're using the same two functions? Well, that's a really good question, and that's because if you pick the correct order, then this integral will simplify and it is very easy to solve. But if you pick the wrong order, then this integral becomes extremely difficult to solve. So picking the correct first function and the correct second function can either make the integral easier or harder. And of course, we want it easier. So we are going to figure out how we can find out which function is the first and the second. And I use a mnemonic to help me remember, and that is this right over here. It's called elate. I know in a few other online tutorials and a few other books they use a different mnemonic, but overall it's still the same. So the I stands for inverse trig functions, L stands for log functions, A stands for algebraic functions, and then so on and so forth. And this should be an L. So first we need to identify what category does x and tan inverse x squared fall in. Well, x is pretty obvious. That falls in the algebraic category. And tan inverse x squared, that falls into the inverse trig category. Now, using this, we already know what our first function and our second function is going to be. Our first function is always going to be the function at the top, or higher than the other function. So that's going to be our first function, and this is going to be our second function. Now we can actually apply the integration by parts formula. We're going to rewrite the first function, which is tan inverse x squared. Always remember this squared, right? And then times the integration of the second function, which is x, minus integration of the derivative of the first function. So derivative of the first function, tan inverse x, and then squared, times, I know, it's a lot, integration of the second function once again. Just to recap, this is our first function, integration of second function, derivative of first function, integration of second function. So now I'm pretty sure we can just go ahead and simplify this. I know integration of x is 1/2 x squared, and then I'm going to rewrite tan inverse of x squared as it is, minus integration of the derivative of this, going to apply chain rule, to tan inverse of x over 1 plus x squared, because the derivative of tan inverse x is 1 over 1 plus x squared, times 1/2 x squared, because once again we said that is 1/2 x squared. And then of course dx. So in this term we have two integrals, an integral of an integral, I guess you could say. And I see we can simplify a few things. That 2 and that 2 get canceled out. I'm going to rewrite this. So over here, I just rewrote it, and you might notice that I didn't write the bounds. So the bounds in the original problem are 0 and 1. And the reason I left out the bounds is that I wanted to focus on the integration of parts first and then just deal with the bounds later. So now we can deal with the bounds. Our bounds are 0 to 1. And in this case, our bounds are also 0 to 1. And I see that we have a 1/2. We can just take that out because that is a constant. And now we can start simplifying. So we have equals 1/2. So that one goes in here. So we have 1 squared times tan inverse of 1 squared is going to be pi over 4 squared. And there is a squared over here minus 0. And then I'm just going to rewrite this as it is. I'm going to simplify this. So currently we have simplified it to this. This is of course not our answer. We still need to solve this integral over here, and that is the tricky part I was talking about earlier. So let's actually get a new page and explain it a little better over there. So here is the integral we are going to work with. This pi squared over 32, I'm just going to rewrite it as it is. And I'm actually going to break this apart into a really neat and clever trick. So bounds are going to stay the same. I'm going to break this apart into x squared, or excuse me, 1 plus x squared, minus 1, and then times tan inverse of x over 1 plus x squared dx. And the reason I did this is because I wanted the terms of the denominator to be present in the numerator as well, because I thought we can cancel something out and that would make it a lot easier. So basically what I did, I noticed that the denominator had a 1, so up in the numerator I added 1, subtracted 1, and we're just multiplying by tan inverse x. Now I'm going to split this integral, so we're going to leave that pi squared over 32 the exact same, minus integration of 1. We are going to expand this, so 1 plus x squared, tan inverse x, just distributing it, minus tan inverse x over 1 plus x squared dx is equal to pi squared over 32 minus 0 to 1. Now I'm going to split it into two integrals. So if I split it into two integrals, this and this get canceled, so I'm just left with tan inverse of x plus, and I got that plus because minus and minus make a plus, so plus integration 0 to 1, and I can't cancel anything out from here, so I'm just gonna write it as it is, tan inverse of x over 1 plus x squared dx. And I forgot a dx over here, so I will just add it, so dx. Alright, now we are once again going to apply integration by parts. And we're going to apply integration by parts over here. And you'll see why in a second we're not going to apply it over here, because there's actually a way easier method to apply over here. So let's actually do the hard part first, which is this part. Now we need to figure out what two functions we can use. Over here, I only see one function, tan inverse x, but we need two functions because that's what integration by parts wants. Implicitly, there is a 1 times tan inverse of x, so I'm just going to say that one is a function. And bringing back our mnemonic from above, this one is going to go in the algebraic section, and this tan inverse of x, well, that is pretty self-explanatory. That's going to go in the inverse trig. And of course, this is going to be our first function because it's above, and this is going to be our second function. So I'm going to keep pi squared over 32 the same. I'm going to have minus, I'm going to include big brackets, and now once again we're going to do that whole entire long formula. We're going to rewrite the first expression as it is, so tan inverse x, because that is our first expression, times integration of our second expression, minus integration of the derivative of our first expression, so tan inverse of x, times integration of our second, of our second expression, plus, and I'm going to rewrite this. This is the expression that we have to solve. So this pi squared over 32, once again, stays the same. Integration of 1 dx is just x, so x tan inverse of x, minus integration, derivative of tan inverse x is just 1 over 1 plus x squared. This is just going to be x as said before, so we have an x dx, and this is going to stay the same. Alright, so we're getting a bit closer. I do have to add the bounds. Once again, the bounds are going to be 0 to 1, so I'm going to add 0 to 1. and this also has to be 0 to 1. So solving this, we get 1 times tan inverse of 1, which is just pi over 4. Now, in order to solve this, we are going to apply u substitution. I know there is a lot of formulas in this problem, but we are going to apply u substitution. In this case, let me do it with a different color. We are going to be setting u, so let u equal 1 plus x squared. Therefore, du is equal to 2x dx, and x dx is equal to 1/2 du. Of course, we have to change the bounds, so one of our bounds is 0, so when x is 0, u is going to be 1 plus 0, which is just 1. When x is equal to 1, u is going to be, and I'm just substituting it right there to find the value of u. And when x is going to be 1, u is going to be equal to 2. So I'm going to rewrite that as minus integration 1 to 2, because those are our new bounds. This x dx we found, which is 1/2 du. And that 1/2, I'm going to take it out. Du over here, and our denominator just going to be u because we set that equal to u. And now we can finally close these brackets. I'm going to rewrite this over here. So pi squared 32 minus pi over 4 minus 1/2 natural log of u. We're going to close our curly braces. And once again, I'm going to rewrite this as it is. Now I'm going to substitute these to finally solve that integral. Pi squared over 32 minus pi over 4 minus 1/2. We're left with ln 2 minus ln 1, but ln 1 is just 0, so I'm just going to leave it over there, and then plus this. Alright, so we're at the final stretch. I'm going to expand this minus, or I'm going to distribute this minus. And over here, I think you guys might have guessed, we're going to use u substitution again. So I'm going to let u equal to tan inverse of x, because when I take the derivative of that, I get 1 over 1 plus x squared dx, and that is basically this part right over here. And of course, we have to change these bounds again. So when x is equal to 0, u is equal to tan inverse of 0, which is just 0. And when x is equal to 1, u is just equal to tan inverse of 1, which is pi over 4. So our new integral is going to be 0 to pi over 4, and that is going to be u du, because this is u, and then that is du as we found it out. This is pretty simple to solve. So integration of u du is just 1/2 u squared. Going to take that 1/2 out because it's a constant, and then I'm going to substitute these pi over 4 and 0, the bounds. So when I substituted pi over 4, I got pi squared over 16. We can simplify that to pi squared over 32. And finally, we can add these two together, and our final answer will be pi squared over 16 minus pi over 4 plus 1/2 ln 2. And that is finally our final answer. So this problem was extremely long, but the gist of it was just to apply integration by parts, which we needed to apply twice, and u substitution, which we also needed to apply twice. And just remember, integration by parts, we're going to be using that I-late method over here just to figure out if a function is the first function or the second function. I hope you guys enjoyed this video, and I'll see you guys for the next one. Bye!